This is the pre-lab lecture video for experiment 15, where we're going to be looking at thermodynamics. And in this lab we're going to be determining the delta G, the delta H, and the delta S for the dissolution of barium iodate. So we're going to be measuring the free energy change, the change in enthalpy, and the change in entropy for dissolving barium iodate. And so the reaction of barium iodate dissolving is shown here, where it breaks up into barium 2+ and 2 equivalents of the iodate ion. And we are going to be measuring the delta G, the delta H, and the delta S by determining the solubility product constants for the dissolution of the barium iodate at several different temperatures. Now, to help you with the background for this lab, you should refer to the recorded lecture videos on thermodynamics for more information. So again, we're going to be determining the change in entropy and the change in enthalpy for the dissolution of barium iodate. Let's begin by looking at the delta G. One of the ways that we can calculate the delta G is using the equilibrium constant. And so delta G is related to the negative RT ln of K, where R is the gas constant and T is the temperature, and K is the equilibrium constant for the reaction. In this next part, we're going to switch from the natural log to the log. We're using base 10. So we're switching from the ln to log, and the ln of K is equivalent to 2.3 times the log of K. So we've just simply made that substitution in here. Now I'm just solving for the log K. So I'm dividing both sides by negative 2.3 times RT to isolate the log K value. And using our other equation for delta G, where delta G equals the delta H minus T delta S, if I multiply through by -1, then the negative delta G equals negative delta H plus T delta S. So notice I can now substitute in this negative delta H plus T delta S into this negative delta G form of the equation up above here. Now I've just pulled out the negative delta H, and I've separated these into two terms. And when I did this, the T's were canceled out for the numerator and denominator, and we still have the T divided by T in this first component here. But I've just separated out these two components, the negative delta H and the T delta S. Now in this next form, the same equation, I've just factored out, or I've just pulled out the inverse temperature. And the reason why I did this is to put the equation in a form that looks like an equation for a line. So the log K would be the Y, the M, or the slope, would be the negative delta H over 2.3 R, and the X would be the inverse temperature, and the Y-intercept would be the delta S over 2.3 times R. So in lab, once you determine the equilibrium constant at several temperatures for this dissolving of the barium iodate, you'll be able to plot the log K versus the inverse temperature. And from the slope, you should be able to get the change in enthalpy for the reaction, and from the Y-intercept, you'll be able to get the change in entropy for the reaction. So from the slope, the delta H can be calculated, and from the Y-intercept, the change in entropy can be calculated. Now be careful, a common mistake in this lab is that the students use the delta H as the slope value as the delta H, and they also use the Y-intercept as the change in entropy. But you have to isolate those terms. So for example, here I've got the equation for my trend line. The slope is negative 2,946.6 is my slope. My slope is equal to the negative delta H divided by 2.3 RT. So I have to multiply both sides by 2.3 RT to isolate my change in enthalpy, and also divide both sides by -1. So now those will cancel out. So my delta H equals the 2.3 RT times 2946.6. So I have to solve for the delta H because this whole term is my slope. And I also have to do something similar for the change in entropy because this whole term is my y-intercept, but I want to know the delta S part of it. So to find my change in entropy, I have to take the y-intercept and multiply it by 2.3 R. So remember, we're trying to determine the equilibrium constants at several temperatures so that we can get the change in entropy and the change in enthalpy. But the barium iodate is a colorless ion, and when it dissolves, you have a colorless solution. And we need to be able to determine the concentrations of the barium 2 plus and the 2 iodate so that we can calculate our KSP values. So what we're going to do is we're going to convert the iodate ions into I3 ions. And the I3 ions, the triiodide ions, are orange-brown in color. And because they're orange-brown in color, this means that they absorb light. And based upon the amount of light that it absorbs at a particular wavelength, we can determine the concentration of the triiodide that's in there using Beer's law. And if we know the concentration of the I3 minus, we can back calculate the concentration of the iodate. So just to kind of re-summarize, our first reaction is where we're dissolving the barium iodate, but the iodate that's produced is colorless. So we're going to take that iodate that's colorless and convert it into the triiodide form. We're going to determine the triiodide concentration using colorimetric analysis, and from the concentrations from the absorbance we will be able to back calculate the amount of the iodate ions. And when we determine the concentration of the iodate ions, we can use that to solve for the KSP at that particular temperature. So we said we need to be able to calculate the concentration of the triiodide, because remember, we're taking the iodate ions and converting them to the triiodide. Well, to be able to determine the concentration of those triiodides, we need to compare those values to some standards or to some knowns. So we are going to create a calibration curve using several known concentrations of triiodide. And we will measure the absorbance of those solutions at the various concentrations to create our trend line. And remember, we'll be using Beer's law, where the absorbance is proportional to the concentration. So the higher the concentration, the more that the compound will absorb. So once we have this calibration curve, we will be able to measure the absorbance of the triiodide solution of our unknowns. From the absorbance values, we'll be able to calculate the concentration from our trend line. Once we have the concentration of our triiodide, we can back calculate the concentration of our iodate because it's a 3-to-1 mole ratio. Once we have the iodate concentration, we can also calculate the barium concentration because that's a 2-to-1 mole ratio, and we can substitute those values into our KSP equation to find the KSP values at a particular temperature. Now remember, when we're using the spec 20s, we're going to be determining the percent transmittance of the solution, and then we're going to calculate the absorbance using the equation where absorbance equals a log of 100 over percent T to get the absorbance. Now after we get our delta H and our delta S values from our plot lines, we're also going to be able to calculate our delta G. Now you can calculate the delta G using the equation delta G equals negative RT ln K, or the delta G equals negative 2.3 RT the log K. But this is from a single data point. Instead, we want you to use the equation where delta G equals delta H minus T delta S. If you use the delta G equals delta H minus T delta S, this is based on the trend line because you calculate the delta H and the delta S values at several different temperatures. So this is why getting This is why the calculated delta G values will be slightly different, and why using the data based on the trend line is better for calculating the delta G. Now, a couple of experimental details that we need to look over to make sure you get some good data. Because remember, we're going to be looking at barium iodate dissolving and making a saturated solution. And we're going to be determining the KSP values for this dissolution at several different temperatures. So the saturated barium iodate solution is already prepared for you. You're going to find it in the fume hood. Take 100 ml of the slurry, and you must get part of the undissolved barium iodate to ensure that the solution stays saturated when you heat the solution. So you may want to make sure you get some of the undissolved particles in there, because remember, this is at room temperature, so if you warm it up, more of the barium iodate will dissolve. So we want to make sure there's still some stuff in there to dissolve when you warm it up. Now also too, remember, we're looking at the equilibrium of the saturated solution, so we want to make sure that our solution is saturated. But we also want to make sure that we don't have any solid in there, because if we have some solid in our sample, once we convert the barium iodate to the triiodide, any solid that's left in there will redissolve because you've removed the iodate ions from there. That shifts the equilibrium to the right, so more of the barium iodate will dissolve. And this will give you a higher value of the iodate concentration. So to get rid of any undissolved particles, because we don't want any undissolved particles influencing or changing the saturated amounts, we need to filter out the undissolved particles. So what we're going to do is we're going to take a piece of filter paper and wrap it over the tip of a syringe. And then you're going to secure that filter paper with a rubber band. Now be careful when you're attaching the filter paper. If it's too snug on the syringe, you may have a difficult time pulling up the solution, or the filter paper may tear. Also, do not dip the syringe in the solution so far that the solution goes up over the top of that filter paper, because you may not have a good seal and you may get some undissolved solid particles trapped inside here. So we want to make sure we have a well filtered solution when we draw it up through the filter paper. Also, to make sure that you draw the solution up into the syringe very slowly, because the solution has to pass through the filter paper. This may take some time, so be patient as it soaks through the filter paper and fills up here. And so you have to suck up the solution with the syringe here, and you're going to need 5 ml of your sample. Then once you've collected your 5 ml, then you remove the filter paper and the rubber band and use that 5 ml sample for the rest of your analysis. Now there's an Excel template on Blackboard that you must use to report your data. Be sure to use the slope and the intercept function in Excel to determine the slope and intercept, and not the trend line values. You still need to add the trend line, but using the values from the trend line equation introduces rounding errors that we want to avoid. This concludes our pre-lab lecture for the thermodynamics lab. If you have any questions, please ask your instructor when you get to lab. Also, to be sure to listen to your instructor in case your instructor has any further information that needs to be given to you or any other safety details.